and I want to start with the part of the response as dynamic response. Okay, so we are discussing at the moment the response problem concerning the steady response. I'm sorry, but I have a new system and I'm not sure that this is stable or not. Excuse me. Can you hear me? Can you hear me?
Yes, Chris.
Okay.
Yes.
Okay. And can you see my screen displayed?
Yeah.
But it's very, very slow at the moment. Probably we have connection problem. Okay. Okay. Yeah. We are talking about static response, and in particular, we are now here on discussing the response to a control surface, and we discussed the effectiveness of this surface, and we also discussed the point that this kind of discussion is in a static framework, in the sense that we want to see what happens when you move your control surface and see what happens with respect to your expectation. And typically the expectation is not the fully expected result when one has, because of the consequence of this maneuver is not only an increasing of lift, but also an increasing of pitch moment, which is able to torque your wing. And because of the torque, you have a decrease of the effective angle of attack. This is the motivation. However, I want today to show the general formulation for facing the problem of the effectiveness of a control surface, and eventually the limit case of the reversal of the command reversal. So, excuse me for this delay. Oh my God. Okay. I'm very sorry. I don't know what happens. Okay, this is the case of two-dimensional case. I have upgraded this whiteboard, and this is the last whiteboard. In this last whiteboard, I want to discuss the general case of our formulation. This general case is characterized by the fact that if you consider the maneuver of an aircraft. We have a fuselage, we have a wing, a left wing, a right wing, and we want to perform, for example, a roll maneuver. Roll with respect to this axis, x-axis, and the maneuver is such that you want to roll your aircraft in this way, uh, in this direction, and excuse me, the x-axis is typically in this direction here, is the wind direction, excuse me. And so we want to positively roll your aircraft, so generating an increasing of lift here, so moving up your control surface here, up, excuse me, you want to increase here, so you want to move down, down here, down, down, and up here, up, up here. So you want increase of lift here and decrease of lift here in order to have a roll maneuver. But when you perform this, you are actually also impressing a torque in your wing, and therefore probably the overall effect should be in opposite direction with respect to you are with respect to you are expecting by this maneuver as well. If you consider the rigid body analysis by flight mechanic, you have a principal moment of inertia by in the linearized, of course, linearized description. You have a moment of inertia multiplied by p dot. You have as p, q, r, the three component of the angular velocity, as you know, and this is actually balancing in the linearized version your moment, the global moment, aerodynamic moment with respect to the x-axis. And this is equal to 1/2 rho u to the power 2 surface chord and a CL. Now this CL in the standard vision of flight mechanics is the sum of several contributions like CL delta multiplied by delta plus a CL as depending on the roll motion, so a CLP by P, and in the undimensional version as multiplied by C and divided by 2u infinite. So this is an undimensional and dimensionalizing term for undimensionalizing P. And finally, you have as last CL contribution also the variation of CL as given by P dot, the roll acceleration term, and you have a P dot C divided by typically the acceleration gravity used as undimensional quantity. So in other words, in the flight mechanics world, the performance of CL are depending on the rigid body motion. This is something similar to what we have in aeroelasticity, but in flight dynamics, this is presented in a simplified way by considering the contribution, the motion contribution, collaborating for determining the CL term. Okay, so in flight dynamics, you have something similar you did in aeroelasticity. So describing how these forces are depending on the rigid body parameter like P dot, and also by the angle of attack. So if you assume this description for the roll maneuver, what you expect is to impose this delta in flight dynamics and then see that as effect of this imposed delta, you have a roll velocity P. And in a steady condition, okay? So flight mechanics means, of course, rigid body motion, rigid motion. here. Okay. So rigid motion, and also in a steady condition, the steady condition means that you impose this delta, and you see in steady, after a time, what happens after a time, whenever all kind of dynamic or transient phenomena are filtered out. So in steady condition, one has that 0, because P dot is 0, you have that 0 is equal to dynamic pressure term, so essentially CL 0, and therefore one has 0. 0 is equal to CL delta, CL CL delta by delta. Oh, sure. Excuse me. Plus CL P in steady condition, C by Q infinite plus 0, because P dot is 0 in steady condition, and therefore here you have the opportunity to determine your P in steady condition as given by, so the angular velocity is given by minus CL delta divided by C. This is very typical analysis in flight dynamics. Q infinite by C and by delta as well. So delta positive means that you are moving this right wing aileron down, and you are anti-symmetrically moving this left wing aileron up. Okay, and what you expect here is a positive steady angular velocity. But is this what you expected or not? Yes, it is, because, for example, what about the sign of this aerodynamic derivatives? Or derivate di stabilità, as known in Italian language. So you have to ask to yourself, what do you expect to the lift when you move this delta positively? Do you expect an increasing of lift? Okay, this is obviously positive, because you expect an increasing of lift when you have an increasing variation of delta. So this aerodynamic stability derivative is positive. And what about this? This is important. How the lift varies if you consider a positive contribution of P. P means angular rotation around, positive angular rotation around the x-axis. This means you are moving up your left wing, you are moving down your, you are moving up your right wing. For P positive means right wing up and left wing down in an angular motion. Positive means that. And when you are moving the wing up, okay, you are actually decreasing your angle of attack. If you are moving in the right wing, you are increasing. So at the end, you have that this kind of motion are actually inducing a decrement of the angle of attack on the wing, and so the lift will decrease. This implies that CLP is the quantity less than 0. And therefore, you have always positive the numerator, always negative the denominator, and this sign here. And therefore, you should have, as a result of your motion, an steady value of your angular velocity, which is exactly what you expect by using your aileron. Okay, no problem. You have an expected command. But if you perform this analysis in elastic framework, you have to consider in general the following. You have to introduce in the aeroelastic framework not only in the elementary example to the example we did on past Thursday. Our elementary example was the following this year, remember, with the typical section. Okay, but in general, what can we do? In general, we have to consider as displacement in elastic framework this roll maneuver is described first introducing this axis, y-axis, excuse me, zeta axis, and this is the aircraft. We have a positive axis, x-axis, in this direction here. And therefore, we want to consider, just like here, excuse me, excuse me, it's not the correct direction. The positive is on the other side. So inside here, and we want as effect this rigid body motion here with an angle positive in this direction, like a phi angle. So the displacement, the general displacement, the general aeroelastic displacement in any time, so consider also this function of time, is given by the rigid body motion, so consider this shape function as a psi function of x multiplied by this generalized variable, which is the angle phi, plus we have the displacement, the deformation quantity given by the Lagrangian variable by Qn, and then here we have the contribution of the aileron described by a function, an aileron function multiply the aileron angle delta. So what about this function here? So this here, this shape function is exactly this shape function representing the rotation, the rigid body rotation. So this is psi phi. Okay. And what about this? This function here is the following function. Consider this right wing like this. This is the aircraft, and we have a right wing. We have an aileron, and here in this section, plane, we have the following. We have z-axis, and excuse me, this is the x-axis in the flow direction, and here we have that the shape function is something like that. We have a hinge of your aileron here, the hinge, and for representing the aileron motion like this, we have a shape function almost zero, but not zero here in the domain of the aileron. So we have something zero and then a linear rotation. Linear rotation means a straight line representing the rotation. And this is psi delta, function of x. A function which is almost zero, but not zero in the aileron domain. And this is psi delta. So when you have delta, the Lagrangian variable, not zero in time, you are multiplying this shape function, and then you are representing the motion of the aileron itself. Okay? So the overall motion is the sum of these three kinds of shape function. The first one is the shape function characterizing the aileron. The second one is the shape function characterizing the output rigid body motion. And the third one are the typical shape function representing the deformation. So the free body elastic mode shape. Okay, so rigid, aileron, and elastic. Okay, so for n equal from 1 to number of modes. So the rest of the formulation is standard. So you have to build your mass matrix. So you have a mass matrix, but the first two terms of this state space variable is here given by the list of delta angle, first shape function, and then first Laplace variable, rotation angle as second Lagrangian variable, and then the elastic one, Q1, Q2, up to Qn. Now, if we work on Laplace domain, we have tilde, tilde, everything tilde for any Lagrangian variable in time. Okay, so on the left hand side here we have first the mass matrix. So we have as mass matrix the m delta delta term, then we have m delta phi, and then here we have m delta 1 m delta n mode shape. This is the first line of the mass matrix. In the second line we have m phi delta, M phi phi, and here we have the rigid body motion together with the other elastic mode, and so we have 0 because this part of the matrix is diagonal, because we have rigid body motion, we have the rigid body motion, which is a special principal body motion which is orthogonal to any other elastic mode. And so we have 0, but not 0 in the diagonal. In the diagonal we have the generalized first mass, the second generalized mass, and finally the n generalized mass, and then 0 and 0. But here we are not 0, because the aileron mode is an artificial mode. It's not a mode of vibration. It's just a mode associated with the kinematic of the aileron. So you have to consider the general formulation of the generalized mode. So we have phi delta delta, phi delta, 1 delta, and then 2 delta, or the other up to the m, n delta. And for example, you have, remember that phi delta delta is by definition the integral all over the body, the density, and you have to multiply the delta dot psi delta. So after this operation in the V, multiplying this shape function by itself, you have essentially, what is this? This is the moment of inertia of the aileron with respect to the hinge. Okay, but you have also the other contribution. You have m delta phi. You have to multiply your phi delta by psi phi. So this shape by this shape function. So we have in general coupling, and the same coupling, this rigid, this delta aileron shape by the mode shape function, and so on. So this is the final m. This is an yes, it is an n plus 2 by n plus 2 mass matrix, and this mass matrix is multiplied by s square, Laplace variable, plus you have a stiffness contribution. Excuse me. You have we have a stiffness contribution given by for example, imagine to have an hinge with an elastic here, with an elastic constraint between aileron and the rest of the aircraft. And so in this case you have something like m delta delta by omega square delta delta. This is a stiffness, and this is the stiffness associated to the hinge constraint here for the aileron. And then you may assume that the coupling is 0 with the other mode, and you have a 0 here for the rigid roll motion, and you have on the diagonal generalized stiffness like equal to m1 of vibration by the omega 1 elastic mode of vibration, and then all the other in the diagonal up to m and omega n square of vibration, and 0 here and 0 here. This is the generalized stiffness. This is the mass, which is including the aileron effect. Is almost a modal mass matrix, almost, because we have also the control surface contribution, and here you have almost stiffness matrix, because we have again here the hinge contribution, and finally here we have the aerodynamic matrix, and this is built just in a standard way. So you have minus qd, and here you have a generalized term like delta delta, and then you have E delta phi and again E delta 1, and so on up to E delta n, and again you have a E phi delta. Again, in the diagonal you have E phi and E phi 1 and the other. This is the first two line, and you have E1 delta, again up to En delta, and down here you have E1 phi up to the last one, which is E N phi. And this sub block here is the block associated to the mode of vibration, generalized mass matrix. So in the general concept of your generalized aerodynamic force matrix, you have n plus 2 mode shape. Some of these shapes are physical. The first one is not physical, just associated to the aileron. Okay? So this is our left hand side, and on the right hand side, what we have on the right hand side? On the right hand side, we have the command of the aileron. So in the first equation here, the first equation is the equation associated to the control surface motion. And so, as forcing term here in the right hand side, we have the moment applied by the actuator for moving the control surface. So we have the generalized force reduced to the force performing work on this degree of freedom. So we have moment. So you can write this moment here as multiplying a almost zero vector with 1 in the first position and then 0 everywhere. And so this is the Laplace transform of the moment. So we have in this first equation here, you have in this first equation look, you have a moment applied, you have a aerodynamic contribution acting on the control surface given by the motion of all the mode in the aircraft. And of course, what is important in this simulation is the influence of the delta aileron on all the other mode of vibration, including the roll. So I imagine that this term should be important, because this term, this second term, is a term acting on the second equation, which is the roll equation, as due to the motion of the aileron. So you have delta as input and phi as output. So this is the most expecting term on the guide of the aircraft. So this term is actually evaluating the influence on phi given by the motion of the aileron delta. Okay, but in the first equation, you are applying your moment. Okay, and so in the first equation, you are activating the influence. So you are activating this other term here. Okay. But how can we use this general aileron response equation in limit steady case? Okay, so we want not to consider phi as space-space variable, but we prefer to consider p, which is the derivative of phi. Okay, p is equal to phi dot. Okay, and therefore we could look consider here. We could consider here this operation. We could introduce as state space variable p by s multiplied by s for obtaining p, and correspondingly we have to divide all this column by s, so divided by s, divided by s, divided by s, divided by s, and again we have 0 in this second column dividing by s, so this is not influent, this division by s, because we have 0 division by s in this second column. We note that this is the second column, and so we have a division by s which is not influent, and here we have a division by s in the steady condition, division by s, but we have also multiplication by this s, so this is not influent at all. And so we could, after this position, we can evaluate p steady by taking the limit for s going to 0 in the previous equation of motion, and then evaluating p steady. This p steady as s is going to 0, or k in the aerodynamic method is going to 0, will give you an algebraic system by this equation here. And this is the system that so moving this initial part, which is not influent, but just considering this elastic and aerodynamic, steady aerodynamic part, for giving to you this steady vector in terms of angle of aileron, p steady velocity, and q. So you can evaluate p steady, and we can check if p steady is greater than 0, or is an algebraic quantity greater than 0, or if p steady is less than 0. And this is the reversal check. Okay, this kind of generalized study is a way for moving by the steady response to dynamic response. So I want to conclude our reversal study moving to dynamic response problem, and this gave me the possibility to discuss the aileron response as a dynamic problem, in the sense that the response to an aileron control surface is maybe a steady problem, like I have just shown to you, but it may be also a dynamic problem. For example, we have in this introductory example I showed to you, I said that, I'm very sorry because the system is very slow, and I would like to show to you this recap at the beginning. Maybe it's better to ask by this framework and show Okay, in this way it's better. Okay, when I introduce these initial slides, I told you that we will talk about a static three-mass solution and a steady response to control surface. So we concluded this part, and I want to start in this dynamic response part, but I want just to begin this part with the end of the previous part, talking about dynamic response of a control surface. Indeed, uh, we may also to study the dynamic response of a control surface, just moving dynamically the control surface up and down. If you apply a perturbation to your aircraft, for example, moving the control surface up and down, for like a bang-bang maneuver, aileron up and aileron down uh, with a discontinuity in this angle, you may to to be interested to see what is the aeroelastic dynamic response to this dynamic input, not static dynamic input. But the system is very easy to be considered because you may directly assume this model here. If you consider this model here for dynamic response, this equation, oh my god, I can't find the cursor on my excuse me. I can't see my stick in the whiteboard. I'm very desperate. I'm sorry, but I can't use my stick at the moment. I don't know why. I'm sorry. Okay. Okay. Thank you. Okay. So I have this system, this general dynamic system, and we could call this matrix as a matrix applied to all the state space for giving us this. And therefore, by this system, like this star, we can introduce easily the output of the system in terms of delta angle, phi angle, q1, q2, qm as equal to s square m plus k minus qd by the generalized aerodynamic force matrix to the minus 1 applied to 1, 0, 0, and the moment at the hinge of the aileron. So we have a single input, multiple output system, dynamical system, and this is our transfer function matrix, or vector better in this case, but you should also consider this included in the definition if you want. So you have a vector, a transfer function vector, such that multiplied by m is giving to you the Fourier Laplace transform of your states, including delta angle, the phi, and also the generalized coordinate for representing the motion. So this is a dynamic aeroelastic system response. To a moment, better torque actuation. For example, you could impress your system in time a moment like up and down and then zero. This is a classic bang bang input. Okay, that is the first case of dynamic response. But this is not the most interesting dynamic aeroelastic response. The most interesting one is the gust response problem, which is the second kind of dynamic response. So the first kind of dynamic response is easy, and this is the transfer function. The gust response is the response to an encountering gust in flight condition. And we want to study this as a very interesting case. Now are 5 o'clock. Before talking about the gust response, I want to give you some design issues on swept angle. Wing swept angle in sweep angle of wing in aeroelasticity. This is the sweep angle, lambda. I want to discuss with you the influence of this angle on aeroelastic issues like the divergence, like the aileron reversal. How is important to have a sweep angle for improve or not improving the capability of the wing to with respect to the divergence or with respect to the aileron reversal. Okay, so this is our discussion the next time before talking about gust response for an aircraft. So thank you for your attention and see you this Tuesday.
Arrivederci.
Arrivederci.